So in our previous lectures, we've learned how if you dissolve a ionic compound in a common ion, solubility will decrease. Today we're going to talk about how pH can affect solubility, because it most definitely can. Now, before we can jump into that, we need a few friendly reminders about acids and bases. So an acid is something that can donate a hydrogen ion. This reaction right here, we're going to look at, this is formic acid. It's an acid because it will donate a hydrogen ion, and then that would be your conjugate base. Now, when any acid donates a hydrogen ion, it will attach to water and form hydronium, which is H3O. Now, a lot of times acid reactions are not written including water. They would just be written like this. HCO2 aqueous is gonna form CHO2 aqueous plus H plus. Hydrogen and hydronium are the same thing, but that's where the hydrogen ion is going. It does attach to water and form that cation, hydronium. But this and this, they are interchangeable, same thing. This is the same reaction as that. And weak acids do not fully dissociate, which means this formic acid will donate some hydrogen ions and will form some of these, but it doesn't fully separate. So there will be some of these left over, which means it comes to an equilibrium, and we can write K expressions for them. We call it Ka because it's an acid. So here's formic acid's dissociation. Water is not included in the K expression because water is a liquid. You don't include liquids in K expressions. So if I added hydrochloric acid to this system, what's going to happen? Well, the first thing you do need to remember is that HCl is a strong acid. Strong acids fully dissociate. So if there's not a reverse arrow, it will fully separate into hydrogen ions, or hydronium, and chlorine ions. So what is that going to do to this system? Well, if I put HCl into this, that means I'm adding hydronium ions, because HCl dissociates into hydrogen, which remember we said hydrogen, hydronium, same thing. So I've added hydronium ions. So that would increase the concentration of hydronium, which will cause the reverse reaction to occur. So you're going to have more formic acid molecules be formed. If I added sodium hydroxide to this equilibrium system, now sodium hydroxide is a strong base, which means it fully dissociates. So NaOH will form sodium ions and hydroxide ions. I've added sodium and hydroxide to this system. I hope you remember by now that sodium ions are always aqueous. They will not react with anything. They will stay dissociated in water always. They're one of our naps. But the hydroxide ion will react with hydronium. Hydroxide is a base. Acid plus base will neutralize each other. And what happens when that is formed, I'll write it out down here. Hydronium plus hydroxide, that's my acid. Hydroxide's my base, and you just have to know those are acids and that's a base. And again, what do acids do? They get rid of hydrogen. So that will make water and water, because the hydronium will lose an H and form H2O. The base will take the H, which forms H2O. So the hydroxide will neutralize the acid, which means if the hydroxide is neutralizing the acid, the amount of hydronium will decrease. Hydronium will go down. If your hydronium ions decrease, that will cause this forward reaction to happen. You've lost products. So this really fast was just a refresh of acid and bases, how they work. Now let's look at them with an equilibrium system and how pH can affect a system. That's not just formic acid. Okay, so here we have this equilibrium system for chromate and dichromate. Chromate is a yellow color, and dichromate is orange. This is its equilibrium reaction. So if I dissolved this in sodium hydroxide, what is going to happen? Again, when you read this, you have to recognize that it's a strong base, which means you're adding it to sodium ions and hydroxide ions. Sodium ions, again, they're totally aqueous. They're never going to do anything. But the hydroxide ions will neutralize the hydrogen ions, which means the concentration of H will decrease because they've been neutralized by OH. If your hydrogen ions have decreased, that's going to make it favor the reverse reaction. If the reverse reaction gets favored, I'm going to make more chromate. So the amount of chromate is going to go up, which means it's going to be more yellow, less orange. So if I dissolved this in an acid like HCl, again, you have to recognize HCl is a strong acid. So hydrogen ions, chlorine ions. Chlorine ions anions aren't going to interact with those anions. They're not going to interact with H because H and Cl are strong acids, so they stay separate. But you have added hydrogen ions. So you've added a reactant, which means the concentration of hydrogen ions has gone up. If you increase a reactant, it's going to favor the forward reaction. If the forward reaction becomes favored, we're going to make more dichromate. So dichromate will go up, making this more orange. Now, what if I dissolved this system in barium nitrate? Barium nitrate, you should recognize when you see this that anything with nitrate that's in NAPS, that means it's completely aqueous. So you are putting it in a solution of barium ions and nitrate ions. We know nitrates are NAPS. They won't form anything with anyone, but it's the barium we need to think about. And the clue to figure this out is that I gave you KSPs. So barium chromate has a KSP that's 1 × 10 to the negative 10. That's pretty small. A small KSP means that it's going to form a precipitate. It forms a solid. Barium dichromate has a large KSP, which tells you it's aqueous. So if I add barium ions to this solution, based off of this information, that tells me I'm going to make barium chromate solid. Because it's got the small KSP, it's going to precipitate out and form a solid. If the chromate ions have become a solid, they're not aqueous anymore, which means the concentration or the molarity of the ions have decreased. If the molarity of the chromate ions have decreased, because they're all a solid now, that's going to make it favor the reverse reaction. And again, it'll make it more yellow. Let's look at a few more examples of how pH can affect solubility. If you're in my class, this is in your practice packet. So gallium hydroxide has a KSP of 7.28 × 10 to the negative 36. That is really small, which means it is very, very little will dissolve. This is pretty insoluble. It stays solid. So under which circumstance will the gallium ion concentration be the highest? So what I'm trying to figure out here is which one of these are going to make the reaction forward favored. What's going to make that forward reaction happen? Because that will increase the amount of gallium ions. It is not going to be A, because this is KSPs are given for when you dissolve something in water, and we can see it's really small. But let's look at B and C. What if I dissolved it in HCl? So again, if you dissolve something in HCl, that means you're putting it in hydrogen ions and chlorine ions. Chlorine, there's nothing in this problem that tells us that chlorine's going to interact, so we can assume it's not. But we should look at this and recognize that hydrogen ions will neutralize the hydroxide ions and form water, which means the amount of hydroxide is going to decrease. If the amount of hydroxide ions that are present decrease, that's going to drive this reaction forward. It'll make it forward favored, which would increase the amount of gallium ions. So it's most likely B. But let's just check, why is it not C? Well, if I put it in sodium hydroxide, again, I'm adding sodium ions, which will not do anything in solution, and hydroxide ions. If I add hydroxide ions, I've added a common ion. We should know by now that adding a common ion decreases solubility. What does that mean again? That even less would dissolve. You've increased the amount of OH, so it's going to be very reverse favored. It's very insoluble already. It's even less insoluble in sodium hydroxide. You're going to have even less ions if you put it in there because you're starting with a common ion. So B would be the right answer. And then let's look at this one. So this is we've got two reactions going on, and we have the F ion in both. So predict how the solubility of YF3 changes if you increase or decrease the pH of the solution. You do need to remember that if you increase pH, that means your solution is more basic. So the amount of hydrogen ions have decreased. Okay, so if I put this in a basic solution, something with a high pH, that means the amount of hydrogen ions have decreased. If the amount of hydrogen ions have decreased, that is going to cause reaction 2 to be forward favored. And it will make more hydrogen ions. That means it's also going to make more fluorine ions. So the concentration of fluorine ions will go up. If the amount of fluorine ions go up, what does that do to reaction 1? That makes reaction 1 reverse favored, because you've added a product. If reaction 1 is reverse favored, then the amount of YF3 solid will increase. So if I make more solid, we would say that solubility decreases. Now let's do the reverse. If I put this in a solution that has a low pH, that means it's acidic, the amount of hydrogen ions will go up. That is, you putting it in a solution with a lot of hydrogen ions. We're going to see the opposite happen. If we start with a lot of hydrogen ions, that's going to drive reaction 2 in reverse. It will be reverse favored. If this reaction 2 is reverse favored, the amount of fluorine ions has decreased. If the amount of fluorine ions has decreased, that would make reaction 1, which has fluorine ions in the product, forward favored. That's forward favored. The amount of solid YF3 would decrease because it's favoring that forward reaction. So we wouldn't say solubility decreases. Solubility would actually increase because you would have less precipitate or less solid. So that would increase your solubility. So I hope in this video, these examples help you recognize how pH changes, or adding an acid or adding a base, same thing, can affect solubility in equilibrium systems.